Welcome to This Explainer. I am absolutely thrilled you're joining us today because we're going to tackle one of the most powerful, yet honestly kind of wildly overlooked architectural blueprints in software engineering. We're talking about the Memento Design Pattern. By the end of our time together, you're going to completely master production-ready state management. And hey, we aren't just sticking to the basics here. We're going to scale our understanding from a simple user interface interaction all the way up to massive distributed enterprise systems.
Okay, let's dive right in. Here's our agenda for today. We'll start with the universal undo button, then we'll meet the three key actors of the pattern and actually build a memento in Go. After that, we'll look at advanced production patterns with Command and Facade, go over how to avoid some critical production pitfalls, and finally, we'll scale the whole thing up to distributed architectures.
All right, Section 1, the universal undo button.
Now, I want you to think about this for a second. How would you actually implement Ctrl+Z from scratch? Seriously. Every single time you press Ctrl+Z in your code editor, or every time a database cleanly rolls back after an error, or, when your favorite video game saves your exact progress right before a massive boss fight, the memento pattern is silently doing its job behind the scenes. But I challenge you to think about how you'd build it. How do you snapshot an object's state without exposing all of its private internals to the rest of the app? And how do you keep a history of those states without instantly creating a massive memory leak?
Well, the first instinct for a lot of developers is what we call the naive approach, direct field copying, right? Just copy the object properties over. But honestly, this completely shatters the moment your application scales. Direct copying falls apart with complex nested objects, it really struggles with computed states, and worst of all, it totally violates private field encapsulation. You're exposing everything. The Memento approach, on the other hand, is highly principled. It gives us a way to cleanly capture the state, store it externally, and restore it seamlessly, all while keeping those private fields strictly private.
Moving right along to Section 2, the three key actors.
To really wrap your head around how this works, think of a memento as a photograph. It captures a moment in time exactly as it was without needing to understand the scene itself. I mean, you don't ask a photograph to explain what's inside it, do you? You just look at it. The snapshot is completely opaque to the outside world, and that brilliantly illustrates the absolute ultimate form of encapsulation.
So let's meet the three mandatory actors that actually make this possible. We've got a little cast of characters to make this work without violating the single responsibility principle. First up, we have the originator. Think of it as the storyteller. This is the main object whose state we actually want to save, and it's literally the only one that knows how to create and consume mementos. Second is the memento itself, which acts kind of like a scroll. It's a super lightweight, completely opaque snapshot of one single state. And finally, we have the CareTaker, acting as our librarian. The librarian manages the history list of these scrolls. And this is absolutely crucial. The librarian is completely blind to the actual secrets written inside them.
All right, Section 3, building memento in Go. Let's take these abstract concepts and translate them into real working Go mechanics. We'll start simple. Step 1, you define your core business state, maybe just using a basic string to get started. Step 2, you create the memento struct, which is your lightweight snapshot container. Step 3, your originator struct implements specific save and restore methods. This gives the originator total absolute control over creating that memento. And finally, Step 4, your CareTaker steps in. In Go, this is usually just a slice or a stack that blindly manages those memento structs without ever inspecting their contents. It just holds on to the results.
Which brings us to Section 4, Advanced Command and Facade. Now, that simple string example is great for getting the basics down. But real production code bases, they need robust, flexible application-level transactions. You can't just pass strings around. In production, Memento is almost always combined with the command pattern to handle multiple, varied types of state. We use a command interface essentially as an untyped state carrier alongside a Memento facade that gives us a single, clean API for automated saving and restoring. Historically in Go, returning an empty interface offered incredible flexibility, but it meant we had to rely super heavily on type assertions. Luckily for us, if you're using modern Go 1.18 or higher, you can implement this exact same pattern using generics to completely eliminate those clunky type assertions. It's fantastic.
Also, the specific underlying data structure your CareTaker uses to manage these snapshots makes a massive difference. You have a few options. If you use an indexed list, it's perfect for version history, but you really have to watch out for unbounded memory drawth. A stack gives you that natural last-in, first-out behavior, which is exactly how our Ctrl+Z scenario works, but it limits you to sequential reversal. Finally, for high-performance real-time systems or game engines, a bounded ring buffer is absolutely vital. It enforces a strict memory limit by simply dropping the oldest states as the new ones come in.
Let's move into Section 5,
Avoiding production pitfalls.
Okay, so the crucial point here is the operational reality check. What happens when things go wrong? I want to give you a very strong warning right now. An uncapped CareTaker is a 3 a.m. out-of-memory pager alert just waiting to happen. You absolutely must cap your max history size. Also, remember that mementos live entirely in memory, so if your process crashes, boom, your entire history evaporates. No way around it. Furthermore, if your application has extremely large states, snapshotting is going to become way too computationally expensive, and if state changes happen at a super high frequency, like every single keystroke, you literally must debounce those inputs, otherwise snapshotting will totally crush your CPU. And one last thing, if your state spans multiple microservices, a single node memento isn't going to save you. You'll need distributed sagas instead.
And that leads us perfectly into Section 6, Trust and Distributed Scale.
Now, what's really interesting about this is how interconnected architectural patterns actually are. Have you ever worked with event sourcing? Because event sourcing is literally just the Memento pattern handling millions of events at scale. Instead of saving a massive current state, distributed systems like Kafka, Axon, or Event Store DB store a ledger of every single state transition. By replaying that ledger, they can reconstruct any past state. This just proves that the fundamental concept of Memento works just as beautifully at a global enterprise scale as it does in a single UI thread.
To wrap up our technical exploration today, I want to leave you on a slightly more philosophical note. The Memento Design Pattern is fundamentally about trust. It is such a beautiful example of encapsulation and separation of concerns. The originator trusts the CareTaker entirely to safeguard its secrets, but fundamentally does not trust it to read them.
As we finish up this explainer, I really want you to reflect on your own code bases. Think about how you are managing state today. If your application crashed right now, does your CareTaker have the exact secrets needed to rebuild your system's history? Thank you so much for diving deep into the Memento pattern with me today. Keep exploring these concepts and keep making your software more robust and more elegant.